variation. This is the power frequency variation. And you already know, because the frequency is basically the dynamic equilibrium between the load and power generated. So as you already know, in big power plants, suppose there's a hydropower plants and there's a speed governor and water is flowing, it is keeping, the speed governor is keeping the speed constant. So that's why you have the constant frequency 50 Hertz or 60 Hertz. But if there is a sudden change, big change on the load, and if load is increased too much, then it will generate the currents which are flowing in the stator winding, and large torque, electromagnetic torque is generated, which will be a braking effect on the rotation of the rotor. And then the meantime governor is taking effect, flowing more water, so that the speed is remain constant. So this is basically for it. This effect is not much seen for large generators, but there may be some cases, but the effect you see, false zero crossing. So if variation in frequency is there, so your equipment may malfunction because it is the false zero crossing, and it's the same type of thing which we have seen in voltage notching, that if there is a big notch crossing the zero, so it will be false zero crossing. Okay. So according to Hydro-Quebec statistics, Hydro-Quebec is a utility company in the province of Quebec. In the province of Quebec, we have around 44,000 megawatt of power generation in province of Quebec. And I will discuss that thing after 2-3 lectures, that this is very interesting, that in the Quebec 100% electricity is generated by non-polluting sources. Okay, 44,000 megawatt. Out of 44,000 megawatt, 40,000 megawatt is hydro electricity, and 4,000 megawatt is wind energy, and there is very less solar energy, but that I will discuss after 2-3 lectures. I will discuss the reason why it is so. So in the province of Quebec, 100% electricity is pollution-free, clean energy. Okay, so Hydro-Quebec is the utility company for the province of Quebec, and according to Hydro-Quebec statistics, the average of fundamental frequency on network should be as follows. Main network, 60 plus minus 0.6 Hertz, that is 1% variation. Okay, or between 59.4 Hertz to 60.6 Hertz during 99% of the time. So this is their standard. Isolated networks in remote areas, because there are so many remote areas, and I will discuss that also later on, why there are so many remote areas and why we cannot connect the grid to those remote areas, because they are thousands of kilometers away and it is not economical to put a transmission line there. So there are 200 communities living in the north of Canada which are not connected to the main grid. They are totally dependent 100% on diesel generators. So that is the topic. After 2-3 lectures I will be discussing about this thing. So in isolated networks in remote areas, 60 plus minus 4 Hertz, or between 56 Hertz to 64 Hertz. So this is what they, because it is a small power network, and in a small, if you have variation even small, so that counts. According to Indian Electricity Grid Code, enforced by Central Electricity Regulatory Commission, okay, permissible frequency band on the national grid, this is because you have 50 Hertz, so 49.9 Hertz to 50.05 Hertz. So this is the Indian Electricity Grid Code. For isolated network, it is not defined. Right now it is, because perhaps in India there are not many Because 2 years ago I heard that all areas connected with the main grid now, but I don't know in India. So maybe perhaps it is not that important because there are not many isolated communities perhaps in India. But if they are there, so they are working accordingly. Okay. Power frequency variation may be caused by a fault on high voltage transmission line, because if power frequency is changing, tripping of large load, loss of control of large power. So these may be the reason that power frequency variation may be there. Now, if you see the different factors concerning the harmonic, there are so many factors. So we need not to go to all those factors. I will just discuss the basic one. As you can see that THD for our power quality course, total harmonic distortion, is very important, and you people already know this is the formula to calculate total harmonic distortion of voltage, and the same type of equation you get for the current. So here VH, you can see this is the RMS voltage of individual harmonic component, and V1, or you can say I1, V1 is basically RMS voltage of fundamental component. Yesterday one student was asking what is RMS value, but that is very reasonable question to ask some student. Where perhaps Professor Madhusudan was also there. So please don't worry about this. This is very valid question. Actually, what you can say RMS, physically what you can say RMS value, if there is certain resistance and current is flowing, so RMS current will heat up, the resistance losses will be the same as almost DC current flowing. So that is why we call it effective current or RMS current. So physically you can say, otherwise V divided by root 2, that is the mathematical equation, that is fine. But the losses caused in the resistance by RMS current, suppose 10 ampere RMS current is flowing through the resistance, it will cause the same losses as 10 ampere DC current is flowing. So physically, approximately, we can say certain like this, okay? So RMS voltage of V1, RMS voltage of fundamental component, and same thing for TSD of current. So I1 this is the RMS current of fundamental component, and IH is the RMS current of individual harmonic component. So now you see harmonic here starting from second, H is equal to 1 is the fundamental frequency. So starting from second harmonic, and here it says infinity, but recently they have made changes in IEEE standard 519 in 2022 and 2014, that they are saying it is good enough to go until 50th harmonic. So we need not to say that infinity or above 50th harmonic. After 50th harmonic, that is good. Perhaps because standards are made by a group of academicians and engineers from the industry, so they know very well their work. So that's why perhaps there might be certain reason that they say, okay, harmonics above 50th harmonic may not have very important effect on the system. So perhaps they have limited it up to 50th harmonic. Okay. So this is just, I tell the student, okay, in 5 minutes calculate TSD of voltage if this is the, so you need not to calculate, but later on we will have. Another important thing is the TDD. So generally, as power quality engineer, I have seen in most of the papers they don't mention TDD, right? They are concerned because THD is basically for a smaller system like our system, like not in megawatt or big right system, but TDD is used, total demand distortion, used for large industrial systems, okay, assessing long-term performance as it relates to the system's full load capacity. THD is used for smaller, less complex system. So our system, what we work in our labs for small system, the THD is good enough. But if you are talking about large, big system like 2 years ago, one of my students was doing internship in a company in the north of Quebec. Rio Tinto is a big Australian company. They do aluminium products. And they have a very big plant in the north of Quebec. Now there may be a problem there because of the tariffs posed by President Trump. So they were saying, okay, 50% tariff on the iron products which are coming from Canada to US, and 25% and 25% aluminium. And then because he was not satisfied, President Trump, so he said, okay, now we will have 50% tariff. So everybody was very scared, especially those companies who are working in the, even I think this Mittals, they were having one iron ore plant there. So for many years they are there. Nobody thought about this thing that Canada is totally dependent on US to supply this steel and aluminium. So now, I don't know, they have not yet resolved the problem. So in Rio Tinto, so they have big transformers in multi-megawatt range transformers and system for processing aluminium. Okay, so there they have a lot of parallel product lines, and big transformers are connected in parallel. So there we should be worried about the phase shifting, which we will be discussing soon. Phase shifting between the transformer. And this is what I was telling earlier yesterday in my speech, that one engineer suggests the management, okay, we can have similar type of system for second line of production. That we will come later. But talking about TDD, this is for large industrial plants, and you can see this is the same as we have in THD, starting from second harmonic, and but here you see this is the RMS value of maximum fundamental load current, calculated as the average of maximum monthly demand currents for 12 months. So this is how, instead of putting I1 here, which is RMS current of fundamental component, so here it is more complicated to calculate IL, and in some cases data may also not be available, so it's not that easy to calculate TDD. For our system, THD is good enough, but TDD also has the same limits. Okay, so I will come to that later. So TD also has the same limit, like we always talk 5%, like a THD maximum, but individual harmonic current limit may be different. So this, we will see the table, what is that table. So this is the difference between THD and TDD. Now, the mathematical part of the RMS current we were talking about, we were saying, okay, RMS current may have effectively same losses in the resistance and the DC current. But if you see, this is how we calculate the effective RMS current. So starting from harmonic 1, there is some echoing effect. Okay. So here you can say first fundamental component of voltage you can take out, then starting from the second harmonic, okay, So this is basically equal to this. It is basically the TSD formula, right? If you take it here and take the square of this, so this is what we have put, this equal to this. Okay, so you can simplify, and finally you can see that this is the relation between the effective RMS value of voltage and TSD of voltage. Same type of equations you can derive for RMS currents also, relation between TSD of current and RMS of current. Now, DIN distortion index, generally in North American paper you don't see distortion all the time. We talk about TSD, but many companies and researchers in Europe, they use DIN instead of TSD. And there is a relation you can see here, it is same as TSD, but here instead of having V1, which is the RMS value of fundamental component of the voltage, you have this series. Okay, so you can take the square of this and you can simplify, you can take V1 out here. Okay, because I hear echo is there, right? Okay. So here you can simplify it by this, this by this, and finally this is the relation between the DIN and the TSD. Okay. Because I hear the echo, but it is fine, it's okay. Sometime it comes the echo, perhaps. You also hear the echo? It's okay, we'll manage, don't worry. Okay, so if you see the relation between the DIN and TSD, this is the relation. So DIN is here and TSD is here, and if you draw the curve for initial some value of TSD, the relationship is linear between the DIN and TSD. And when the TSD value increases, pardon? No, they are using, but some researchers still this is one factor which may have, otherwise it is basically the same thing. You can represent it DIN or TSD, but it is just that the maximum value of DIN is 1. Yeah, if TSD goes very high, you can say DIN is 1. DIN 1 means TSD is very high. Okay, so it's okay. Now see this table. Harmonic voltage distortion limits in percent of nominal fundamental frequency for, this is new, harmonics less than 50th harmonic. Okay, and they also have added, earlier this was not there in IEEE standard 519 1992, this was not there, but I think they have recently added this thing. Otherwise this was there, that bus voltage at PCC is less than or equal to 69 kV. Individual harmonic voltage distortion limit is 3%, and TSD total should be less than 5%. We already know this thing, right? You are already using it in the lab. And if the voltage is between 69 kV and 161 kV, higher voltage, so this limit is reduced 1.5%, and TSD limit is reduced to 2.5%. And if this is very high voltage, more than 161 kV, then individual harmonic voltage distortion limit is 1%. So as the higher voltage is becoming higher and higher, we have a more severe limitation on individual harmonics, as well as TSD also 1.5%, because they don't expect you to have more harmonics on the transmission high voltage side. Okay. And then this is So less than 1 kV, you already know in your lab, you see 8%. I was surprised to see this. So for a smaller system, it is 8%, not 5% basically if you are having less than 1 kV. This is the new I saw in perhaps the new modification. So just check it, okay. Now, odd harmonic current distortion limit in percent. Here TDD is written, but the same limits are for THD also. Okay. So if the size of the system, distribution system increases, because this is the short circuit current divided by the load current. So if short circuit level is increasing, it means perhaps the circuit breaker capacity, perhaps they might be putting more, so that that large system may have large current. So that's why you see starting from less than 20 ratio, it may be more than 1000 here. And this is how the limits are changing here. If harmonic is less than 11th harmonic, like 3rd harmonic, 5th, 7th, up to 11th harmonic, this is 4% for individual harmonic, okay. And then we have, if size of the system is increased, we can go to 7%, for larger size 10%, and if the size is more, then we can go to 15% individual harmonic, while total you see is still for a smaller system 5%, and then larger system this limit is increasing. As far as higher harmonics are concerned, if harmonics are between 11th and 17th harmonic, like 11th, 13th or 15th, those harmonics, limit is to see this is reduced. So if harmonic ranking is increasing, so limit is also more severe. For higher frequency harmonics, limit is more severe. You see here it's 2, then from 17th to 23 it is 1.5, from 23 to 35 it is 0.6, and harmonics ranking more than 35 up to, now we can say up to 50th harmonic, okay, this is 0.3%. Okay, so this is how you can interpret it, that as the system size, distribution size increasing, you can tolerate higher level of harmonics. But as the harmonic ranking is increasing, you have to have more severe limitations on the limit of harmonic, as well as you can see the THD, this thing. This was for voltage less than equal to 69 kV. But if voltage level is between 69 kV and 161 kV, then you see it is half of these. So if the system is 20 short circuit current divided by load current is 20, then instead of 4 you have 2 here, instead of 7 you have 3.5 here, instead of 10 you have 5 here, so half of these here, 15, 7.5. Same thing for other ranges also, see, this is half, instead of 2 you have 1, 3.5, so 7 is 3.5, okay. Same thing here, you see, almost going half of all those values. So if the voltage level is increasing, you have to have a more severe limitations on harmonic, and here you can see also half THD total, 8, instead of 8 you have 4, instead of 12 you have 6, instead of 15, 7.5, instead of 20 you have 10. For the voltage more than 161 kV, these are almost same. Here there is an error, this is 20 here. So, and see, these are almost same, not much change here. So this is IEEE standard 519, recently updated, but these are odd harmonic limits. But if you are having an even harmonics, it will have more severe effect on the system. Even harmonics are not desired, not at all. So they have 25% limit. So whatever values you are having, calculate the 25% limit of that, and that is for even harmonics. Then we can talk about the K factor. So K factor, this is the formula for K factor. Here IH, RMS value of harmonic H, this thing, right? HM harmonic you can say. And starting from 1 to, I think this should, instead of infinity, we can put here 50th harmonic. Okay. I effective RMS, effective value of load nominal current. So what is basically factor K? It represents transformer's ability to handle harmonic currents. And they have standardized values. So engineers in the industry, because you cannot have infinite number of different transformers, so they have put, okay, K factor value may be 4, 9, 13, 20, 30, 40, up to 50. Okay, K factor of 1 is for linear load. So you have a simple transformer, balanced system, linear load, so you don't have to worry about harmonics. So you can have K equal to 1, which we generally do even in transmission and there. While factor K of 50 is of severe harmonic distortions. So if you think then that there is a load is such kind which is generating lot of harmonics, and those harmonics will flow through transformer windings, higher frequency harmonics, so it will have lot of losses, ferromagnetic losses. See, ferromagnetic losses, hysteresis loss and eddy current loss, right? You know the hysteresis loss. What is hysteresis loss? Hysteresis loss is something like this, right? Flux density, relationship between flux density and magnetic field intensity, H. So area within this loop, it represents the losses. So we call this the hysteresis losses. So those hysteresis losses are proportional to the frequency. So if you have the fifth harmonic, suppose you have fundamental frequency. So fundamental frequency, this is 5, you have certain hysteresis losses, eddy current losses. But if you have a fifth harmonic, then hysteresis losses will be maybe 5 times of hysteresis losses of the fundamental frequency. And seventh harmonic, fifth harmonic, if you are having fifth harmonic and you see the eddy current losses are proportional to the square of the frequency. So it means whatever eddy current losses you are having with the fundamental frequency, whatever eddy current losses you are having, you will have 25 times more eddy current losses if you have a fifth harmonic. And if you have a seventh harmonic, then the eddy current losses will be 49 times more, which you are having eddy current losses at fundamental frequency. So this is a very serious thing. So if you are having higher harmonics, they may have a lot of heating. So this is heating up the core, and the temperature of the motor or transformer will increase more. And you cannot have more temperature, perhaps some relay will trip because higher temperature is there, because you have to protect your transformer or motor, you have to protect it from heating up. Otherwise, the insulation may burn down and it may reduce the life of your transformer. So you have to basically derate it, transformer. Sometimes you may not go more than 50% of the nominal load. So this is the importance of K factor here. Now there are different other factors, okay, like different factors concerning the sustained interruptions, outages. Outages means you have long-term outages. When we say outages, it may be in hours perhaps, you don't know, okay. So some indexes, one is SIFI. This index is basically used by managers to manage the system basically. So not as an engineer you will be using, but if you are a manager of certain utility or certain area, so you should be concerned about this thing. So SIFI is System Average Interruption Frequency Index. And what is SIFI? Total number of interruptions per year of clients divided by total number of clients on the network. So suppose we say that there were 30 outages in 1 year, and total number, suppose there were 20 clients on that network. So what will be SIFI? 1.5. So this is the SIFI. And what is CAIFI? Customer Average Interruption Frequency Index. This is system average. Here it is customer average. So total number of interruptions per year of the clients divided by total number of clients affected at least once. Here you don't care. In SIFI you don't care if the certain clients are affected, but here clients affected at least once. So suppose 30 outages were there and only 5 clients were affected. So CAIFI will be 6. So if we say SIFI equal to CAIFI, it means all the customers were affected the same way. But if we say CAIFI is much more than SIFI, like here, 6, it means certain customers were affected more than other customers. Maybe perhaps there is some small community and it is affected in comparison to other communities nearby. So manager has to see, okay, perhaps proper maintenance of local transformer was not done, or there may be some recurring problem, or some trees are there near the transmission line. Every year, 2 times every year in my locality, we have a Hydro-Quebec utility. So they come and check that the trees are not leaning on transmission line. So they cut down those trees so that if some wind is there, a storm, it may fall on the transmission line and it may affect the customers. So this is their work. They make it clear that there is no large tree near the distribution line. Then we have SID, System Average Interruption Duration Index. Duration, see, here we have the frequency, how many times, frequency, how many times, but SID is about the duration, for how long time. Okay, so SID, sum total of duration of interruptions per year of all the clients divided by total number of clients on the network. And CAIDI, customer average interruption duration fixed. So see, this is almost the same, this is the same as here, total number of duration, sum total of duration of interruptions per year of the clients. Maybe for 1 hour, 2 hours, for 10 hours, there was no electricity. But here, total number of clients, here, total number of clients affected at least once. as the same kind of difference in psi-phi and chi-phi we saw, here it is. So basically, if we talk about psi-d and chi-d, it is about the duration, how long the system was down. It means technician was there on the site to see the problem, and he was trying to correct, suppose for example, the transformer. So perhaps technician took long time to repair the transformer. So if the technician is taking long time, it means he has not been properly trained. So he should be trained for the maintenance work, right? So this is the duration, and the frequency is different. So this is the difference between psi-d, chi-d and psi-b, chi-phi. There's a numerical question, but we don't have time for, but yeah, no, they cannot be equal because you see, total number of clients affected at least once. Pardon? Yeah. Yeah. Yeah, yeah.
Not once, maybe so many times.
Yeah. But sometimes what happens, so in Canada sometimes what happens, we have our colony here and then there is a road and the other side there is another colony is there. Sometimes we don't have light but the electricity, but the other side of the road people have the electricity. So we are very jealous why he is getting the electricity, we don't have the electricity, because you can see. So sometime it may happen because they may have different distribution transformer, our locality has different distribution transformer. So it may happen. Okay, so no, I will not go through this. Yeah. Who is waiting? Tea. Oh, tea is very important. We should have tea. Okay, good. Okay, good. Fourier series and we apply it to the periodic function. And what is periodic function? Okay, which satisfies this condition. That is called the periodic function. Okay, so you can see ft0 is equal to ft0 minus t, ft0 plus t. So as an example, you can see at t0, this is the value, t plus t, this is value, this value. So you see, so this is how you represent a periodic waveform. And these are some of the examples of periodic function: full wave rectification, half wave rectification, and cathode ray CROs, sweeping generator. These are all examples of Fourier series: square wave, triangular wave, rectangular wave, right? So these are all periodic function. So Fourier series is represented by, so any periodic function wave you can represent by this Fourier series. Okay, here AV, AN, BN, these are the Fourier coefficients. Okay, W0 is the fundamental frequency. So if you are talking about an integer, so you may have second harmonic, third harmonic, fourth. So these are the harmonic frequencies. Okay, so this is the Fourier series, and you can represent any periodic function using cosine and sine terms. So this is really amazing. Any periodic function can be represented by Fourier series. So how to calculate AV, average value, AK, the coefficient which is related with the cosinus. See, AN is related with the cosinus, BN is related with the sinus. So how to calculate BK for the kth element, right? This is how you can write the equations, how to calculate AK, BK and AB. Now I don't want to, suppose you have this periodic voltage and you have to represent the Fourier series. So first you have to calculate the Vt, this is Vm divided by T multiplied by with time, it is varying. So it is very simple to calculate this Vt. And the average value you can calculate. So these are the formula which we have seen here. You can apply and you can calculate the Fourier series of this periodic voltage. So this is how you see you have some average value is there, right? See, average, as if you can see, right? So this may be come here. So if you take the average, so perhaps Vm by 2, right? So physically also you can see this is Vm by 2. Then AK is equal to 0, BK you can calculate using that equation, this value. So finally, Fourier series for that wave you can write this way. You have the fundamental, you have second, third, all types of harmonics are there. So this is fundamental, and here multiplied by 2, second harmonic, third harmonic, like this. Now, sometime what happens, the engineers in the industry, they don't have much time so to write equation AV, AK, BK and do the calculation. So basically we have to have some easier way to do this. So how you can simplify the task of analyzing and calculating. So there are certain symmetries you have to see. There is a even function symmetry, odd function symmetry, half wave symmetry and quarter wave symmetry. These are the symmetry. If you can find some symmetry in a periodic function wave, so then it will make your task very easy. You may take 1/4 of the time which you were taking otherwise, calculate AV, VK, AK, all those things. So what is even function symmetry? If the function is defined this way, ft is equal to f minus t, right? Like, for example, ft is here, f minus t is here. See, both are equal. This value equal to this value is equal to this. So this is how you can say that it is an even function. ft is equal to f minus t. So if you can see the even function, then bk will be 0 for all k. See, you need not to calculate bk, otherwise you will calculate bk, okay, and finally you will find that it is 0. So you don't have to calculate bk. So you just calculate the average function and ak, which is related with the cosinus. So this makes analysis much simpler. Then if even symmetry is not there, you should check for odd function symmetry. Odd function symmetry is this function ft is equal to minus f minus t. For example, here, suppose this is ft, this is in the negative direction, so minus f minus t because of in the negative side, and here it is negative side. So this is the function. You can say this is an odd function if you can satisfy this thing. So if you see the periodic wave is odd symmetry, odd function symmetry, then you see you don't have to calculate AV. AK also, you don't have to calculate AK also. The only thing you have to calculate BK. So you see, this is how you can simplify the calculation. Just by looking at the wave shape, you can do the calculation fast. Then there is a half wave symmetry. Half wave symmetry, that you shift this wave shape by half cycle and take the inverse of this, then it should give the original thing, right? So this is what you can say. Now you will see, okay, I have a triangular wave, this, so what should I do now? It is not odd or even, so you can shift this axis and you can either have this way, right? So this is what you can see, that you can see here, this is equal to this is equal to this, or you can have, you could have shifted this wave shape here, this x here, so it will give this way, this. So what is basically, this is what? This is the odd function symmetry, right? We have already seen that f. So what you should do here, suppose this is the even function symmetry. This one is even function, right? Because f t is equal to f minus t. So to verify if it is the half wave symmetry, you should shift by t by 2. So t by 2 is here. Okay, so instead of this wave, you have this wave. Take the inverse of this. So it is same as the original, right? So it means it has a half wave symmetry. You shifted it by half cycle, you shifted it by half cycle, took the inverse of this, and it is giving the original function. So this is half wave symmetry. Now you can have, as we have seen here, even function, or you can have odd function. Even function half wave symmetry, or odd function half wave symmetry, right? So if you have even function half wave symmetry, then for even function we have seen bk is equal to 0, av is equal to 0, ak is equal to 0 for k even, right? And So you have to calculate only AK. Okay. If function is odd, then AK will also be 0. For even function, BK is 0. So you do have to calculate only this. If the function is odd, then for all values of AK is 0. So you have to calculate only BK. See? So this is how you have simplified. You don't have to calculate AV, you don't have to calculate all these things. Only one thing you have to calculate. If you can say, this is half wave symmetry. Okay, now we have the quarter wave symmetry. Quarter wave symmetry is a half wave symmetry, and in addition, symmetry about the midpoint of positive or negative half cycle. Okay, so see, does it has half wave symmetry? Half wave symmetry means you shift it by T by 2 and take, so this is the wave shape, take the inverse of this, right? So basically, this is same as the original. So it has the half wave symmetry. Does it have quarter wave symmetry? Quarter wave symmetry means you take this half cycle, draw a line in the middle at quarter wave, and see both sides are symmetrical or not. So if they are symmetrical, you say, okay, this has half wave symmetry as well as it has the quarter wave symmetry. For example, if we see this, does it has half wave symmetry? This is half, this is the value, take the inverse of this. So it comes out as the original. So it has the half wave symmetry. But does it have quarter wave symmetry? You say see in the middle, there is no symmetry, there is no quarter wave symmetry. So though it is half wave symmetry, it does not have quarter wave symmetry. This is half wave symmetry as well as quarter wave symmetry. So if the function is made even and it has the quarter wave symmetry, then you have to calculate AK only for K odd. You don't have to calculate other things. Okay. Same way, if the quarter wave function is made odd, then you have to calculate only BK, this value for K odd. See, this is how you can simplify, you can save your time by not calculating the functions which you know those coefficient might be 0, right? So you don't have to calculate AV, AK, and BK for K even. You have to calculate BK only for the K odds. Okay, now this. Is it odd function or even function? This is odd, right? Because ft is equal to minus f minus t, right? This is coming here. So this is odd function. Does it has the half wave symmetry? This is t by 2. So shift by for half, shift it by c. So this is the wave shape. Take inverse of this. So it means it has the half wave symmetry also. Does it have quarter wave symmetry? This is half cycle, middle of the half cycle. It has the quarter wave symmetry also, right? So what you have to calculate now? You don't have to calculate AV. You don't have to calculate AK, because see what you can see. Okay, if I draw a sinusoidal wave here, right? So it means it is related with BK, because AK is related with the cosinus term, right? So you don't have to calculate AV, you don't have to calculate AK for all values of K, you don't have to calculate BK for even values. Only thing you have to calculate this equation for K odd. Okay, so you can calculate the function IT, just see here, this IM divided, this is T by 4, so you are calculating only for this portion. Okay, so it's not that difficult. You can calculate this and then finally you can calculate BK for this and K is out. We don't have much time, so I don't want you to go through the numerical exercise. See, this is IT and finally this is the periodic Fourier series of this wave shape. So you have third harmonic, fifth harmonic, seventh, all odd harmonics are there. Right? Now I will like to discuss hurriedly the symmetrical component. Okay. Symmetrical component theory for unbalanced non-sinusoidal systems. Okay, because you have studied symmetrical component for unbalanced system, but not for non-sinusoidal. In your undergraduation, you have studied symmetrical component theory, which was good for unbalanced system, but not for the distorted system. So as you know, symmetrical components, these are the equations you can have. So if you have a three-phase unbalanced system, if you have a three-phase unbalanced system, it's difficult to analyze. Therefore, we use symmetrical components. And symmetrical components, you have positive sequence, you have negative sequence, and the zero sequence. So all the VA, VB, VC, they are unbalanced, so you have to use. Now, what is positive sequence, what is negative sequence? See, yesterday night I draw the figure so that I don't waste my time here drawing it again. So you see, these are windings 120 degree apart. Okay, winding A, winding B, and winding C. Then you have some magnet here, North Pole and South Pole. When you turn this magnet in this direction, so first it will induce in winding A, then winding B, and then winding C, right? So you will have ABC, ABC, that sequence. That is called the positive sequence. You can represent it in this way also. There are three vectors, A, B, and C, and your eye is here, observator is here, and it is turning anti-clockwise. So you will have A, after this B will come here, after that C will come. So this cycle is there, ABC, ABC, ABC. That is positive sequence. Instead of turning the magnet in this direction, you turn it in clockwise direction. Okay, so first it will induce voltage in winding A, then C, then B. So ACB, ACB, ACB. That is the negative sequence. Or you can represent here, you have a vector A, you have a vector C, vector B. It is turning in this direction. So first you will see A, after that C will come, after that B will come. So this is what is actually the negative sequence, ACB, ACB, ACB. So each voltage, VA, VB, VC, it is made of zero sequence component, positive sequence, and the negative sequence. Now, if you see here, the same thing. So this is positive, we are talking about positive sequence, ABC, ABC, ABC. So positive sequence, we use A1 here. Okay, see 1, VA1, VB1, VC1. And for the negative sequence, ACB, 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 we use 2 here. VC2, VB2, VA2. So if you see the relation between VC1 and VA1, it is shifted by 120 degree and unit vector. So this is what the A factor we use. A is 120 degree rotation. If we say A square, 120 plus 120, 240 degree, and A3 will come. So if you see this is equal to 1, then you give 120 degree shift, it is A. If you give 240 degree shift, it is A square. And if you put another 120 degree, it will become A cube, which is equal to 1. So what for positive sequence, suppose we say VA1 is equal to V1, then VB1 is equal to this, because we have seen VB, to get the VB1 in VA1 you have to multiply it by A and another A. So that is why we have A square VA1. Similarly VC1, if you see the relation between VA1 and VC1, in VA1 you have to multiply only one A, which will give 120 degree rotation. So that's how it has come like this. VA1, if we say V1, VB1, A square VA1, VC1, A VA1. Okay, to simplify you can write this. Now for negative sequence, VA2 equal to V2. Suppose VA2 we write V2. So if we have to get VB2, then we have to multiply it by single A, which will give 120 degree phase shift. And VC2, so this is 1A and this is another way, A square. So A square VA2, if you, this is VA2, if you multiply it by A square, it will give 240 degree shift. So that is VC2. So this way you can write these equation VC2, A square, VC2. Now the zero sequence component, they don't have the phase shift. See, they are in the same phase, same amplitude. Okay, and they are rotating with the same frequency. So VA0, VB0, VC0, they are of the same amplitude. Okay. So now if we write these equations, which we have seen earlier, see VA1 equal to this one. So you can write these equations using the original equations by putting the value of VB1, VC1, VB2, VC2, like those things. So this is, now if you have to calculate V0, you just take the sum of this. So if you see this V1 plus A square V1 plus A V1, V1 is common, so it will give you 1 plus A square, which is equal to 0. They are 120 degree shift apart, right, this way. Sum of these is 0. So this will all become 0, so V0 will become VA plus VB plus VC divided by 3, because 3V0 here. Now if you have to calculate V1, so here in this equation you can multiply it by 1. In this equation, to get V1 you have to multiply it by A, because then it will become A cube is equal to 1. Here you see it is A here, so you multiply it by A square here. So that way you can eliminate other things and V1 you can calculate. Here to calculate V2, you multiply it by 1. Here it is A, so you have to multiply it by A square in the whole equation. In the whole equation, here A square you multiply it by A. So that other terms will become 0 and you can get the V2. Same equations are for the currents. So this is how you can write V1 equal to this, V2 is equal to this, V0, and same type of equation for the currents. Now if you have a balanced three-phase source, so these are the equation you can write, right? Balanced three-phase source, same amplitude, 120 degree apart, VB equal to A square VA, VC equal to AV. So if you calculate V0, so VB you will be putting here, VA, AVA you will be putting VC here. So what will happen? You see, you take VA out and then you will have 1 plus A square, which is equal to 0. So finally you can say B0 equal to 0. Okay, so if you have three-phase balanced system, zero sequence component is 0. What about V1? So this is the equation for V1. We already know you put the values there, like VB equal to A square VA, right? And VC is equal to AVA, so it becomes A cube. This is also A cube. So finally V1 become AVA. Similarly for V2 you can verify that negative sequence component is 0 if you have three-phase balanced system. So a balanced three-phase source is equivalent to a positive sequence source only, with negative sequence and zero sequence sources being 0. So how you are representing three-phase balanced source? This is the positive sequence, this is the negative sequence which is 0, and this is the zero sequence which is 0. Now if you have a non-sinusoidal unbalanced system, so same equations, you see, IA, we have already seen this equation for I. Similarly, we have equation for IB also, like I0 plus A square I1 plus A I2, the same equation which has been used. Only thing we have done, we have put the harmonics, fundamental, second, third, fourth, all the harmonics. So this is basically sum of all the harmonics. Okay, so this is how we can represent IA current in phase A, which includes all the harmonics. So you can represent it because the currents are unbalanced. Same way IB you can represent by this, and IC you can represent by this. Now you can find zero sequence current of nth harmonic. This is the same equation we have seen. I0 is equal to IA plus IB plus IC divided by 3. This is what we saw. This is the same equation. Only thing is that we have put the harmonic here. If it is fundamental or third or fifth, those harmonics. So total sum of all the zero sequence currents you can represent for all the harmonics. Sum of zero sequence currents of all the harmonics. You can represent by this. Similarly, sum of positive sequence currents of all the harmonics. Sum of all the negative sequence currents of all the harmonics. So this is how you can write. Now I will give you a very simple example. See this example. Here you have to consider a non-linear load introducing the following harmonic current of rank 5, fifth harmonic. Okay, so you have the fifth harmonic and you have to find the sequence of the fifth harmonic. Okay, whether zero sequence current, is it the zero sequence or it is a positive sequence or it is a negative sequence. So you can put the same equation which we have already seen. Okay, so fifth harmonic, so you can write it this way. So because frequency is 5 times, you can write it this way. Now the fifth harmonic for the phase B, this is for phase A, phase B, it is minus 120. The fifth harmonic is there. Why it is minus 240? Because you can say 3 plus 2 multiplied by 120 degree, right? 5 you can write 3 plus 2. So 3 multiplied by 120, it will be 360 degree, which is 0 degree. So it remains only 2 multiplied by 120, so it will give you minus 240. Similarly here, 5 multiplied by 120 and finally plus 240 degree. So you put these values here. These values here. And see what is the value of fifth harmonic, zero sequence of fifth harmonic. Why it is 0? Because IA5, this value, IB5 is minus 240 or this may be plus 120. Right? Minus 240 or plus 120 is same, right? And plus 240, that will be minus 120. Right? If you see the full cycle, 360 degree, so this will be minus 120. So basically, IA5 with 0 degree, IB5 with plus 120, and IC5 is minus 120. So sum will be 0, right? Because they are balanced. Same way, you can calculate I15. So IA5 is this value, 0. IB5 is this, and A is there. Okay, minus 240 plus 120, so that will be minus 120. And here you have A square for IC5. A square means plus 240. A square is plus 240. Plus 240 and another plus 240. So plus 120. This will be plus 120. Is it clear? You just have to put A is what? A is 120, right? A square is 240. A cube is 1, right? We already know. So put these values there and you will see that I15 is 0. Now you calculate this negative sequence with this equation. Okay, let us check it. IA5 is this one, I 0 degree, right? So this is I 0 degree. A square is plus 240, and this is minus 240, plus 240, minus 240, again 0 degree, right? So I 0 degree. Now here A is plus 120, and here you have plus 240, 360 degree, it means 0 degree. Is it clear? So you have to see the phase shifting with A, and finally you will see the negative sequence of the fifth harmonic has the value A. It means fifth harmonic is a negative sequence current. So this is how mathematically you can see if the fifth harmonic is positive sequence, zero sequence, or negative sequence. If fifth harmonic is balanced, this is the condition. If fifth harmonic is balanced, then only it has a particular sequence. If fifth harmonic is unbalanced, then it will have zero sequence also, it will have negative sequence, it will have positive sequence. But here we are talking about balanced fifth harmonic. If the fifth harmonic is balanced, it has the negative sequence. Same way, you can check for seventh harmonic. You see? So yesterday night I was doing this thing. For seventh harmonic, you can write this equation, and 7 multiplied by 120, 6 multiplied by 120 will come out to 0, so it will remain minus 120, so you have minus 120. Okay, same way 7 multiplied by 120, so 6 multiplied by 120, which will come out 0 degree, so you will have plus 120 degree. Although this is a different thing, that now what you can do, you can be smart, you can just draw this diagram. Okay, this is A, IA 7, and this is IB 7, and this is IC 7, plus 120, minus 120, right? And vector is rotating in this direction, so you can say A, B, C, A, B, C. So you can say, okay, this is a positive sequence. But mathematically, if you have to check mathematically, see, I07 equal to this value, put all those values here, and you will see the sum will be 0. Same way, I17, you can check, this is the equation for positive sequence. Put the values of A, plus 120, plus 240 here, and then put IB5, IB7, IC7 here, and you will see that this is the value. And then I27, second harmonic, this negative sequence of seventh harmonic is 0. So mathematically you can see the seventh harmonic, if balanced, seventh harmonic if balanced is a positive sequence. So this is how mathematically you can see the fifth harmonic is a negative sequence if balanced. If seventh harmonic is unbalanced, then it will have zero sequence also, positive sequence also, or negative sequence. So this is a very important thing to verify. And finally, what you can do, you can make a table. Sequence of the harmonic order, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is how you can write the table, and you can see which harmonic is positive sequence, which harmonic is negative sequence. Okay, so now you will say, oh, this is long table. if I want to see the 25th harmonic, do I have to make a table until 25th harmonic? That is not necessary. You just see the equation. For positive, this is the equation. H equal to 3k plus 1. For negative sequence, H equal to 3k minus 1. And for zero sequence, H is equal to 3k. So these equations you can use. Okay, now tell me, if I have 25th harmonic, 25th harmonic, is it a positive sequence or zero sequence or negative sequence? What will be the 25th harmonic? You should be able to tell just right now. It should not be, because you know the equation here. H is equal to 3k plus 1. If k is equal to 8, 3 multiplied by 8 is 24 plus 1. So it will give you 25. It means 25th harmonic is a positive sequence. So you don't have to do all those calculations. That is just to verify mathematically if you are right or not. So this is very important to find. Before you do the harmonic cancellation, you have to know if certain harmonic is a positive sequence or negative sequence. Zero sequence you will know anyway, multiplied by 3 it will be easier. Okay, tell me 29th harmonic. 29th harmonic, what is the sequence? If 29th harmonic is a balanced harmonic, what will be the sequence? Negative. See, so fast you can tell. It's very easy thing. You just have to know the trick, right? Okay, 35th harmonic. 35th harmonic is what? 35th harmonic is negative. Okay, 3 multiplied by 12, 36, minus 1, then only you will get 35, right? So 35th harmonic is a negative sequence, and 37th harmonic will be the positive sequence. See, it is so easy. And now, so we will use this thing later. Now you know the triplet harmonics. Triplet harmonics means multiple of 3. So they may be present in 3-phase 4-wire system. They may be present if single-phase rectifier on 3-phase circuit is there, or you have single-phase induction motor on 3-phase system. Mostly, and there are many other cases, you may have triplet harmonic. So suppose the phase A current is like this. This is phase A current. You can find the fundamental component, and there is a third harmonic. In 1 half cycle of fundamental, you have 3 half cycle, so it is a third harmonic. So this is phase B now. So here again you will see the fundamental, and then you will see the third harmonic. Now for IC, phase C current, and similarly you can find the third harmonic. Although the original current IA, IB, IC, see here you have 120 degree phase shift. See, from here to here 120 degree phase shift here you have. But the third harmonic of phase A, third harmonic of phase B, and third harmonic of phase C, they are in the same phase, same amplitude. So when they come to neutral, if current IA, IB, IC are balanced 120 degree apart, the sum will be 0. But if their third harmonic are coming to the neutral, they are same magnitude but in the same phase also. So that why you will have the sum of IA3, IB3, IC3, you will have sum of these, and in the neutral you may have very high current. So the engineer in a plant should be very careful what kind of load you are having, what kinds of harmonics are being generated. If there are zero sequence harmonic which may flow in the neutral wire, and sometimes they overload the neutral wire and they may heat up, and in very worst cases they may burn also the neutral. So this is very important about the triplet harmonic. Many times we will see that here you have non-linear load which is generating third harmonic. So third harmonic is trapped in delta. So they will not come out here and they will not pollute the network if you have a delta here. Okay, that we will see soon. Now we will hurriedly see this three-phase transformers. Okay, three-phase transformers, sorry. In this we will see, because in India as well as in North America, there are so many different kinds of three-phase transformers are used depending on the application and requirement. Okay, so you have DY1. So we will hurriedly see DY11, DY1, YD1, YD11, DZ0, DZ10, and then we will see harmonic elimination by phase multiplication. So see, if you have this three-phase transformer, if we say DY1, what does it mean? D, capital D. It means on the primary side, it is delta connection. Y is small in small letters. It means, small letters means the secondary side. So secondary side is star connection or Y connection. Now what does it mean 11? 11 specifies the phase shift it will give, right? So you see this diagram, I have already drawn this diagram, and this is the clock. So 12, 3, 6, 9, those are there, okay? And if we say 11, so see there are 12, 360 divided by 12, it means every hour is representing 30 degree, right? So 30 degree represents 1 hour. So if we say 11, this is the reference, okay, and this is, if we say this is on primary side, on the secondary side we have 11. It means secondary side voltage is leading by 30 degree. So if you use this transformer, on secondary side it will give 30 degree leading. If you say DY1, again the primary side you have delta winding, secondary side you have star winding. 1 means here. It means secondary side, secondary voltage is lagging by 30 degree with respect to the primary. So if we say YD1 transformer, primary is star, secondary is delta, and the secondary voltage is lagging by 30 degree. 1 is the lagging here, right? This is the reference, this is the 1. YD11, 30 degree leading. Then you may have YZ1, that is primary is star connected, secondary is zigzag, and then 1 degree, 30 degree lagging. DZ0. So these things are there. So giving you the basic idea, suppose this transformer is delta star connection, DY11 here. So you have three-phase transformer, or you can use 3 single phase transformers. Technically there is no difference. If you use 1 3-phase transformer or 3 single phase transformer, technically there is no difference. Only difference is you have 1 box of 3-phase transformer. Sometime that transformer 300 MVA, 400, 500 MVA, there is one company ABB, Asia Brown Boveri, but now it has been purchased by Hitachi Energy. So we have a big plant there in Montreal. So they make big transformers. Sometimes the transformer is as high, even higher than this room, and maybe almost cover this room, maybe more than half of this room size. So they make such a big transformer, 3-phase transformer. And if you have this kind of transformer, it is very difficult to transport this transformer. You need special means to transport that transformer. So this is a big advantage. Although the efficiency is high of single 3-phase transformer has higher efficiency than 3 single phase. 1 3-phase transformer, big box, but 3 single phase transformer, small box, their efficiency is little bit lower than 1 3-phase transformer. And then what if you want an emergency transformer, if you have a 1 big 3-phase transformer, does it mean you need another such 3-phase big transformer which will cost a lot? But if you have 3 single phase transformer, then you need another small single phase transformer to replace if there is some repair. Moreover, it is easy to repair single phase transformer. It is very difficult to repair 3-phase transformer. So these are some advantages and disadvantages of 3-phase transformer or single phase transformer, right? Sometimes what we do, okay, there is a community and which has some houses, and suppose it has, it needs requirement of say 60 megawatt of power, so you need transformer. But then you see then in future more residences will be added, so you may have more requirement. Perhaps instead of 30, you may need 90 MVA transformer. So what you can do, initially you don't want to invest on 3-phase transformer for 90 MVA. It will be very costly investment in the beginning. So you can start with only 2 single phase transformer, and you can have, instead of having delta connection, you can have VV connections, and which will give you 58% of efficiency. So this is what, and then after few years you can buy the 3rd transformer. So this is how you can delay the capital you are investing. So this is in parallel of this. This may be 1 single phase transformer. This is parallel with this. This is another single phase transformer. This is in parallel with this. This is another single phase transformer. So this is how you may connect. So if you are looking for single phase transformer, this is the relation V1 by V2 is equal to N1 by N2, you already know. And V1 on primary side we use capital letters. On the secondary side we use small letters. So you see, you can write this relation, and then VAB equal to this. If you see this phasor diagram, this is VAN, VBN, and then VCN. So to calculate VAB, you take minus VBN and then sum of VAN and minus VBN, it will give you VAB. So basically VAB is leading 30 degree with respect to VAN. So this is what we have written. This is VAB, this is VAN plus 30 degree, and you simplify, you put this value here. So finally it will give you, M is the transformation ratio, right? And divided, if you say capital M is equal to M by root 3, so this is the global group transformation ratio. So you can write this And the primary, we know already in single phase transformer, N1 I1 is equal to N2 I2. Okay, so this is how on the primary side I1, see IAB is flowing in this direction in the primary. Oh, what happened? Some air is coming. Okay, so this is IAB current in this winding and IA current in the secondary, IA current here. So finally, using this equation, you can write, similarly you can write for this, similarly you can write for ICA. All these are the current in the primary of the single phase transformers. Now IA is equal to, this is the anti-current, sorry it is taking long time to describe. IA is the primary line current, which will be equal to IAB is going in this minus ICA. Okay, so IA is equal to IAB minus ICA. Now you put the IAB value, ICA value, and finally you can find for a balanced system, you can write this equation, and that you can see in this diagram also. IA is here, this is IC minus IC, sum of this, it will give you IA minus M, IA multiplied by M. So this is what we are writing. Okay, but for balanced system, zero sequence currents are zero. Okay, now if you have an unbalanced system, you can write IA equal to this, the same symmetrical components. Okay, and then you can write IC1, IC2 equal to this, IC0 equal to, because IA0 equal to IB0 equal to IC0. Then you can simplify negative value, and then here you can see 1 is here, and A, if you subtract IA minus IC, so I1 minus A, IA1, and 1 minus A square. So you can calculate here, this is A square minus A square, sum of 1 and minus A square, 1 minus A square, which will give you plus 30 degree shift. And 1 minus A, this will give you 1 minus A, this is minus 30 degree phase shift. Okay, so what you can see, IAB is the current, this is the equation we have seen in single phase transformer, and IA, if it is distorted, it has IA1, I2, IA0. So zero sequence current is present. So if we say IAB, here you see zero sequence currents are present, IA0, IB0, IC0. But if you calculate IA using this equation, okay, zero sequence currents are absent here. It means in this transformer, if you have a non-linear load here, unbalanced non-linear load, so you have all kinds of harmonics and sequences, then zero sequence currents, third harmonic, they are trapped here, but they are not polluting the network here if you are using delta. Okay, so what is important here, if you have positive sequence current, if you on the secondary side, when you bring it to the primary side of that transformer, it will get a phase shift of minus 30 degree. And if you have a negative sequence current on the secondary side and you bring it to the primary side, IA capital, then you will have positive plus 30 degree phase shift. This is very important to know, because we know seventh harmonic is what? Positive sequence. And fifth harmonic is a negative sequence. So in the secondary side load, if it is generating seventh harmonic current, so when it will go other side, primary side of the transformer to the network, then the seventh harmonic will have phase shift of minus 30 degree. And fifth harmonic is a positive sequence. When it goes to the primary side of the transformer to the network, it will get plus 30 degree phase shift. So this is very important to know. Later on we will use this technique for harmonic cancellation. So two important effects in DY11. Positive sequence and negative sequence components rotate in opposite directions. Minus 30 for positive sequence for seventh harmonic, plus 30 degree for the negative sequence, fifth harmonic. Zero sequence current is absent in the primary line of the currents. You see, in IA, this is the primary side current which is going to the line of the primary side. There is no zero sequence currents. They get trapped by the delta connection. So in delta connection, you have the current IAB, right? It is trapped here. You see the zero sequence current is here. So it means all the zero sequence currents are trapped here. So they are not going out. If the zero sequence currents are not unbalanced, then you will have other things, right? Now, same way you can analyze DY1, which is also very popular in India also. DY11, DY1, these are popular transformers in India also. Okay, so engineers should know the characteristic of those transformers, and they have to choose which transformer is proper for your plant, what kind of harmonics are there, right? So this is just an example of DY1. And in DY1 we know the secondary side voltage is lagging behind 30 degree by the primary side voltage. This we have, that is why we have one here, right? Now if you see the line side of the current of DY1 transformer, if you have positive sequence current, then it will have plus 30 degree. It means the seventh harmonic will be shifted by plus 30 degree, while the fifth harmonic will be shifted by minus 30 degree. While in DY11 it was 0, seventh harmonic was shifted by minus 30 degree and fifth harmonic was shifted by plus 30 degree. So you have to see the difference. Okay, seventh harmonic plus 30 degree, fifth harmonic is minus 30 degree. So this is, we have seen. Now we have another transformer, YD11. This is the characteristic, how the phases are shifted. YD11, it has this characteristic. Then we have delta zigzag DZ0. 0 means there is no phase shift between the secondary side voltage and the primary side voltage, right? So we don't have time to analyze. Finally, you can see there is no phase shift in secondary side voltage and the primary side voltage. You can see AB is his, AB here, phase AB, here like this. There's no phase shift. But you have to see the advantages of zigzag. Advantage of zigzag we have already seen earlier. No core saturation even with half-wave rectifier or DC component. So this is the advantage of zigzag connection. On secondary side, if you have a zigzag connection, then your core will not be saturated. Okay, transform, because there is no this third harmonic. Okay, no zero sequence current in delta. This is the way. But if you have YD11 or YD1, zero sequence currents are trapped in the delta. So although they are not going out, but they are heating up the transformer. Right? So this is the disadvantage. But if you are using zigzag connection, even here you don't have the zero sequence correct. Okay? And there is no phase shift if you have DZ0. So I will not go in much details of this, although I have put it in the notes. So you see, 7th harmonic, and this is the 5th harmonic, no rotation of positive or negative sequence harmonics. This is DZ10, so this is 60-degree phase shift between the secondary voltage and the primary voltage. That is, the secondary voltage is leading by 60 degrees to the primary voltage. And then you can see the rotation of positive sequence and negative sequence. Now this comes a very interesting things. Okay, it's a harmonic elimination. By why we were studying all this phase shift. So now is the time to apply whatever theory we have learned to see how we can use. So this is what I was talking yesterday when I was giving a speech. Okay, there is a factory plant, there is one line of production, and it is generating some harmonic 5th, 7th, but they are not polluting much to the network. So engineers and everybody is happy that it is not much pollution. Now the time comes to put this secondary line of production, and then that is the time an engineer has to see seriously whatever load, non-linear load you have, what kind of harmonics are generated by that load and how much, and they are going to the primary side and they are spreading around the internal distribution system of the plant. Although presently this is not serious, but if you put the second line or third line of production, then it becomes the serious matter. Okay, so if the engineer says, okay, first line of production we already have and it is not giving much problem, so we can buy the same equipment for the second line. So because we don't have any problem, so we put the same thing for the second line. And I told you that this is the worst decision which can an electrical engineer take. So he has to be very careful to think about this. What is the harmonic situation? So suppose we have DD0 plant here, transformer, delta in the primary, delta in the secondary, and 0 degree phase shift. Now you have non-linear load here. So 5th harmonic and 7th harmonic are generated here, which will be transferred here, I5, I7, which will go here, I5, I7 in all the three phases, A, B, C. Now you have similar transformer here, DD0, suppose we have DD0 here, and these loads are identical. It is generating I5 and I7, which is transported here, I5, I7, which will go here, this way, I5, I7. Now you have 2 I5 and you have 2 I7. See? So this is what is happening. All the harmonics are adding up. because the engineer said, okay, because first line is working fine and the second line should also working fine. And I was surprised to see that 2 years ago, as I told you, one of my students, he was working as an intern in the company Rio Tinto in the north of Quebec. It was a very big plant. Each transfer was multi-megawatt MVA size transformers. And he was showing me the diagram. And he told me, Professor, you told me in the course this thing, and I see now there are 6, 7 multi-MVA transformers, and they were having phase shift with respect to each other. So this is not only for small load, even for large size load also it is very important to see what harmonics are being generated. So we know that if we have similar transformer for similar type of load, it will generate a lot of problem. So that's why we take the example of DY1 transformer. Primary is delta, secondary is star, and there is one means the secondary voltage is lagging behind 30 degree with respect to the primary voltage. So will it be able to cancel 5th, 7th harmonic or not? This is what we have to analyze. An engineer has to see this. So you see, we have D0 connection. First transformer. This is the primary side current. Okay. Secondary side, because this is DD0, there is no phase shift, so it is in the same phase. Secondary line current, secondary side current is given by this. Now, suppose your nonlinear load is generating 5th harmonic, secondary side 5th harmonic, and this is the equation for 5th harmonic, which you transfer to the primary side. This is DD0, there is no phase shifting in the current. So they are in the same phase, 5th harmonic, right? Now see the second transformer, DY1. This is the primary side current of the second transformer. And in the secondary side, this is one connection. The secondary side voltage is lagging behind 30 degree. So the current is lagging behind 30 degree. Okay. Now let us see the 5th harmonic. What will happen to the 5th harmonic of the second transformer DY1? Okay, so we were having minus 30 degree. Now the 5th harmonic is there. This is the phase shift. This is how much? 150 degree. 150 degree, right? Now when we bring this to the primary side, this is the secondary current. When you bring it to the primary side, so what we saw for DY1 transformer, 5th harmonic is the negative sequence. Let us go and see DY1. DY1. This is DY1. 5th harmonic is the negative sequence, minus 30 degree phase shift. So from the secondary current, 5th harmonic, when it comes to the primary side, minus 30 degree phase shift. So see, minus 30 degree phase shift. This is as it is here. And when we are coming to the primary side, we are writing minus 30 degree phase shift. So this is 150 and this is minus 150, minus 30, so minus 180 degree. Okay, so the source current from the first transformer and from the second transformer, 5th harmonic. So from the first transformer, there was no phase shift. DD0 transformer, and second transformer DY1, it has minus 180 degree phase shift. So 5th harmonic is cancelled, right? So this is the advantage. Instead of using second DD0 transformer, we are using DY1 transformer, which is cancelling the fifth harmonic. Same thing, you want to try for seventh harmonic, but you can try, go to your home and try for seventh harmonic. Actually, it will cancel the seventh harmonic also. But it will not cancel this 11th and 13th harmonic. It will again cancel 17th and 19th harmonic. So other harmonics are also calculated this way. So I will not go through again this thing. How much time is left? When I have to finish? 1, okay. Okay, but let me see. Because I have another important topic to discuss. Multipulse transformers. Yeah, I am supposed to teach it today. But it's okay, I will just give you the basic idea. Okay, then I will continue it tomorrow. Okay. So it's a very important topic of multipulse methods. Okay, just another 15 minutes and I will then continue it. Multipulse methods. Okay. So there are so many things, different kinds of transformers I wanted to discuss. So let us see the application of multipulse methods. There are a lot of applications here. As you can see, their application is in variable speed drive. Actually, everything is related to the power quality, and it is a very hot topic, multipulse methods. Lot of people are working, and every day new patents are coming out for multipulse methods. Okay. So application are lot of application of multipulse methods, like in variable speed drives, HVDC, chemical industry, electroplating, battery chargers, uninterrupted power supply, high power induction heating, converters for aviation industry. See, everywhere nowadays multipulse techniques are used. These are known as rectifiers, fed by three-phase source. So if you are having rectifiers, there are some power quality problems. On AC side, voltage and current harmonics are generated, poor power factor. We already have the idea of rectifiers, right? And on DC side, you have the voltage ripples. If the rectifier was already installed, many methods are available to improve power quality, like, you can put passive filter, active filter, hybrid filters, right? But in certain cases, the capacity of these filters become the same as rectifier capacity. Okay, it causes the following problem, increases the cost, because now you have some problem, you find the solution, and the solution is costing the same as the original equipment, right? So increase in cost, increase in losses, increase in number of components, causing the decrease in system reliability, because you are putting another equipment with lot of components. So reliability goes down. Therefore, for new installation, it is preferred to modify the total concept. The technique is called passive wave shaping. And what is the advantage? Simplicity and economic. Passive wave shaping is based on magnetics in three-phase AC system. Therefore, together the system is called multipulse, multi-phase multiplication. There's a lot of development going on in this area. Recently, many articles, even few years back, we wrote a very big review paper on multipulse technique with Professor Bhim Singh, me, and we people wrote a very, and you will find so many articles and so many multipulse techniques. Two major advantages of multipulse system: decrease in current harmonics on AC side, decrease in voltage ripples on DC side. See, this is the example which we have already seen. See, this is DY1 transformer and this is DD0 transformer. Just now we discussed this thing, right? So you have identical equal loads here on the side, and this is the transformer DY1 and this is DD0 transformer. So if you write the equation of current here, this current is proportional to the fundamental, 5th harmonic, 7th harmonic, 11th harmonic, and if you write I2, it is proportional to these things, but see the sign. So if you take the sum of these, this will cancel out, this will cancel out, and 11th harmonic is added. Similarly, 13th harmonic as it. So it means that is not helping in 11th and 13th harmonic, but again on 17th and 19th harmonic it is cancelling. Now the problem is that sometimes load may not be equal. So what is done, you have a single load supplied by DY1 and this is DD0. So this is what, this is diode bridge rectifier, this is diode bridge rectifier, and this is the same load, but you see there is a phase shifting. Here 30-degree shifting, here is no shifting. So basically the voltages coming here, so see 30-degree phase shift between the two voltages. So the ripples will be generated here on this side, which has the instantaneous 30-degree phase shift. So voltages are not equal, so there may be some circulating current problem. So that's why we use interphasing transformer to smooth out the operation. If the converters connected in series, there are certain advantages. You don't need interphasing transformer if the converters are connected in series and you have higher voltage available. What are the disadvantages? Reduced loss current, increase in losses. If the converters are connected in parallel, advantage is increased load current. Disadvantage, you need interphasing transformer and you had, for parallel, you have lower voltage. In general, now in DD0, DY1, we saw 30-degree phase shift, which is helping in cancelling the harmonics. In general, the minimum phase shift required for cancellation of current harmonics in converters with 6-pulse waveform, this is 60-degree, divided by number of 6-pulse converters. Like for example, in our DD1 and DD0, we used 2 converters, 2 6-pulse converters. So if we are using 2 6-pulse converter, which is giving you 12 pulses, right? 6 multiplied by 2, that is 12. So you will have, here you have 260 divided by 2. It means you need 30-degree phase shift, and this is what we gave, 30-degree phase shift. In DD1 and DY1 and DD0, we gave 30-degree phase shift, multiplied 12 pulses, 360 degree. If you have 3 converters, 6 pulse converters, then 60 divided by 3, which will give you 20-degree phase shift. So if you have 3 6-pulse converter, you need minimum 20 degrees. You can have more, but minimum you need 20-degree phase shift. And 3 6-pulse converter, it means 18 pulses, right? So 18 multiplied by 360 degree. If you have 4 converters, 24 pulses, then 4 here, it will give you 15-degree phase shift, multiplied by 24 pulses, 360. If you have 5, then 12, so divide by 5, 12 degree. So this is how you can, if you have 6, then 10 degree phase shift and 36 pulses. So this is how you decide what is your objective, right? So if you are having one converter of 6 pulses, then this is the formula that what harmonics it will generate. It will generate k equal to 1, so 5th, 7th, 11th, 13th, 17th, 19th, those harmonics are generated with one converter of 6 pulses. If you are having m converters of 6 pulses, so this equation can be written like this, and amplitude is this. So if you have, it means if you have 3 converters, so for k is equal to 1, 6 multiplied by 3, so 18k plus minus. So if k is equal to 1, see you have minimum 17th harmonic. 3 6 pulse converter means 18 pulses. In 18 pulses, minimum you will have 17th, 19th, and then 35 and 37th. See, this is a big advantage. If you are using 3 converters, 6 pulse converter, you are having 18 pulses. But you will have 60 divided by 3, 20 degree phase shift. So between the 3 converter, you should have 20 degree phase shift to get this advantage that so many harmonics are removed of this amplitude. Okay? So, okay, I think I should stop here for today, and we will continue with this tomorrow. It's okay? Yeah. Okay, sir. Thank you.